All right, let's continue on here. The next topic is empirical formulas. Now, we should tell you what the empirical formula is so that you know what to look for when you're comparing this, say, to the molecular formula. So the empirical formula is nothing more than the simplest formula with the lowest whole number ratios of between the atoms in the compound formula. So here we've got three examples. We've got these examples here with Ca and S, CHO and CH. So what we'll do here is I'll go ahead and do these problems for us. I'll do the work here along the side, and then you can compare each step. I encourage you to look through the problems here, and if you need to, go ahead and slow down the video, press rewind, watch it as many times as you need to so that you can get the content correct. Okay, so here we go. So the main thing that we want to do here is, I'm going to go ahead and put this down here in the center, is we want to be able to make the following process. So notice how we've got percentages provided to us. What we want to do immediately is check to see if you have 100%. So if you have 100%, and so here's the thing, if you got 100% overall, the one thing you want to do is you want to change that percent sign, you want to change it to a gram sign. And so that's what we're going to do first here. We're going to go ahead and check that. So we go ahead and add the numbers up, 55.6, 44.4. That actually adds up to 100. So I'm essentially going to do the following. Not even going to think about this. I'm going to change this percent sign to a gram sign, change this sign here to a gram sign. And what I'm going to do now is I'm going to convert each of these grams, these masses, I'm going to change them to moles. So the way that we're going to do this is we're going to address these one by one. And so here, what I'm going to do overall is I'm going to go ahead and start with the calcium first. And the next thing I'm going to do here, if you look at the very top, the pathway here, now that I've changed every percent sign to a gram, what I'm going to do now is I'm going to take that value and I'm going to convert all of these from grams, I'm going to convert them to moles. In order for me to do that, I need to divide each of these masses by the molar mass of the individual atom. So what I'll do here is I'll just rewrite everything else. 55.6 grams, and this is going to be of calcium. I'm going to go ahead and divide that by the molar mass of calcium, but I'm going to use dimensional analysis. So here, for every 1 mole of calcium, you can look it up on the periodic table, that number there should be the following. It should be roughly about 40 grams of calcium. So at this point, what you'll see here is we can cancel the grams of calcium, and so what we're left with is the moles of calcium, and that's kind of what I want at this point. If I go ahead and do this, do the math, multiply across, I'm going to take the 55, multiply by 1, that'll give me 55.6 in the numerator, and I'm going to go ahead and divide that by 40. And so if you do the math here, what you wind up getting is 1.39 moles of calcium. Okay, we'll do the same thing for the sulfur. So here we've got 44.4 grams of sulfur, and then we're going to divide that by the molar mass of sulfur. So 1 mole of sulfur has a mass of 32 grams. Again, we can cancel out the units of grams and sulfur, and that would allow us then to have the following number here. So we'll take the 44 multiplied by 1 divided by 32. And so that number there should give us 1.3875. In fact, that's very close to 1.39 if we're going to put the number to 2 sig figs after the decimal. So if I do that, that'll give us here a 9, and this is going to be moles of sulfur. So that now that we've got that, what we need to do is get a mole ratio between the two compounds, and so that means we have to look at the mole numbers. We look for the smaller number, and since these numbers are both the same, we're going to divide it by 1.39. So both of these values will be divided by 1.39. on both sides. And so when we do that division, make sure it's moles that we're going to divide by. That will allow us then to cancel the unit of moles on both sides. And then the final number that we've got here overall should be equal to 1. And this is going to be 1 calcium atom. And that's going to be 1 calcium atom in the formula. And then for the sulfur, that'll be 1 sulfur as well. But that's going to be 1 sulfur atom. That's going to be in the formula. Here at this point, what you want to do is remember that a compound is going to have the positive atom come first, followed by the negative in this format here. And so we got to ask ourselves between the calcium and the sulfur, which one's going to be the positive atom? Well, we know that calcium is a metal, so metals will give electrons, giving them a positive charge. And so the first atom here is going to be the calcium. So I'm going to put calcium here, followed by the sulfur. And so since we only have one copy of each atom, this number here is referring to the mole ratio. So there's a ratio of one calcium atom in the formula for every one sulfur atom in the formula. So our final formula here is going to be CaS. And so I'll clean it up and just say CaS. And so here is our empirical formula, which I'm going to abbreviate EF. And this is the simplest formula that we've got. And you can tell that it's the simplest because we've got a subscript of 1 for both of these atoms. Okay, so let's go ahead and take a look at the next atom. So let's take a look at this next atom here. We've got 3 atoms overall in this particular compound. So I'm going to go ahead and do the work here and quickly check. 48 plus 8 is 56 plus 53. Add them up. That's 100% overall. So we're going to do one quick change right away. Change these percentages to grams. And then we're going to treat all 3 separately here. So I'll do the first one at the very top. Let's go ahead and do carbon first. So here for this particular problem, overall, we're going to do the carbon. So carbon here is 48.6 grams of carbon. And we're going to go ahead and divide that by the molar mass. I'm going to go ahead and do this here in one step. So divide this by 12 grams of carbon. And then I'm going to do the same thing for the hydrogen. 8.16 grams of hydrogen divided by the molar mass. That's 1 gram of hydrogen. And then for the oxygen here, oxygen has a number here, 43.2 grams of oxygen. And we're going to divide that by 16 grams for the oxygen. So here, grams of oxygen cancel. Grams of hydrogen cancel. And the top for carbon, grams of carbon cancel. So this is going to give us here at the very top, if we do the math all the way through, is going to give us the following numbers. So now what we want to do is we're going to look at all of these mole numbers, and we're going to look for the smallest number. In this case, it's 2.7. So we're going to take the 2.7 and use it to divide all 3 of these numbers. And so I'm going to go ahead and do that. I'll use blue. So I'm going to take 2.7 to divide the 2.7 at the bottom. 8.16, I'm going to divide that by 2.7. And it should be clear here, this should be moles. And then in the top 4.05, I'm going to divide that by 2.7 moles as well. And that's going to give me a resulting number. That number that comes out is going to be the number of atoms in the formula for that given element. So you should get the following. Now you can see here the resulting numbers is for the oxygen, we get 1. We get 3 hydrogen atoms and 1.5 atoms of carbon. Now you can't have a 0.5 atom, so what we'll need to do here is we're going to have to multiply this number times 2. And so we'll do that here, and I'll say times 2 this one. But if you do it for the 1 atom, you're going to have to do it for the other atoms as well. So we'll do this here, we'll say times 2 as well, times 2. And so overall, for the carbons, we're going to wind up getting here a total of 3 carbon atoms. For the hydrogen atoms, we're going to get 6 hydrogen atoms, and for the oxygens, we're going to get 2 oxygen atoms. So when we look at this here, our final number here is going to be carbon, hydrogen, and oxygen. We want to put the order of atoms from least electronegative to the most electronegative. That means the most positive type of atom to the most negative type of atom. And so carbon is the least electronegative, and so that carbon would go first. Since there are 3 of them, you can see that because of the calculated value you've got up here. We can definitely bring this 3, bring it down, and we'll put a subscript here of 3 for the carbon, followed by the hydrogens, and that'll be a 6, followed by the oxygen, that'll be a 2. This value here is the lowest number of whole numbers between the carbon, the hydrogen, and the oxygen. So this particular number here is the empirical formula for this particular compound with these percentages. So let's go ahead and move on to the next problem. So now we'll turn our attention to a compound here that has carbon and hydrogen with these specific percentages. If you add them up, it does equal 100. So we're going to do one quick thing right off the bat. We're going to come in here and take the percentages and turn those into grams. Then immediately we're going to convert from grams, we're going to convert this to moles for each of the atoms. So we'll start off with the carbon atom first, and the carbon atom here should have the following. So in this particular case, I divided the mass of carbon by the molar mass of carbon. That gave me 6.8 moles of carbon. Took the mass provided here for hydrogen divided by molar mass of hydrogen. So that gives me the number of moles. I look at these two numbers here and look at the smaller one, that's 6.8. So I'm going to use 6.8 to divide both. So I'll do that in red here. I'm going to divide the top number, 6.8 moles, and use that same number to divide 18.3. Here the unit of moles cancel, and so that'll give me a number. That number in each of these cases, in the top case, it'll give me the following. So that'll give you one atom of carbon in the formula, and over here when we do the other one, that'll be 2.7 atoms of hydrogen. That's very close to a 3, and you could always multiply by 2, but when you do that, you're going to wind up getting here, you're going to wind up getting here 2 of the carbon atoms down here. So what we'll do here is we're going to say this is approximately equal to 3. And so when we write our formula, the formula should be CH3 as the empirical. All right, so here in this particular problem, we're going to be doing molecular formulas. We're going to try to find it. They're giving us information here. We have an empirical formula of CH3, and we have a molecular mass of 30 grams per mole. So we have to use this information to get what we need. And the way we're going to do this is we're going to start with taking the empirical formula and figure out what is the mass of this empirical formula. So that's where I'll start here. And so I'm going to go ahead and take the formula here, which is CH3. So put CH3. And so the mass here for the carbon, that means we're going to get 12. For the hydrogen, we're going to get 1. Since there's 3 copies, we're going to do this, add them all up. So that should give you an overall mass here of 15 grams per mole of CH3. And so what we'll do here is say, okay, well, there has to be a relationship between this particular compound formula. This formula here happens to be the empirical formula. So when I look at the empirical formula, its mass, I can relate that to the molecular formula mass, and then I can notice here, if you look at the ratio here, you've got 30 in the molecular and 15 in the empirical. Molecular is a multiple of the empirical, so the relationship here is a relationship of 30 to 15, and another way of writing that is 30 divided by 15, and this is equal to a 2. So this 2 is essentially known as the multiplication factor. And so this factor is what we're going to use to multiply the empirical formula. Since we already know the empirical formula is CH3, what we'll do is we'll take this formula, we're going to write CH3, and then we're going to come in here and we're going to say times 2 times 2. So this 2 comes from the relationship between the molecular and the empirical. And so when we do that, the carbon here should become a C2, and then the hydrogen should become an H6. And this number here is known as your molecular formula. And that's how you would find that. So the next type of questions we're going to get are the types of reactions. And so remember, there were 5 of them that we needed to know about. Let me put them on the screen and go over them really quick. So here are the 5 different reactions. You've got a synthesis reaction, a decomposition reaction, a single replacement reaction, a double replacement reaction, and a combustion reaction. So the difference between all of these are the following. So let me just write down the generic format here. So whenever you have a synthesis, what you've got is 2 discrete elements, and these are going to combine to form a compound AB. Here in this format here, the A has a positive charge, the B has a minus charge. If you go over here to the decomposition, this particular compound or this reaction is going to be the reverse of the first one. You're going to start with a compound AB, and it will break apart into A and B, reforming the initial elements that you had. In this particular case, remember, A is positive, B is negative, so when you do that, the charges over here will have the respective charges overall. And then with the single replacement, what you've got here is you're going to start off with a compound, let's say AB. There'll be another element, C, and what will happen here is that C will replace A, giving you CB, and then you're going to have A. In this case, A still retains the charge of positive, but the C here comes in with positive and B still retains the charge of negative. For a double replacement, you've got two separate compounds, let's say AB and a CD. And then since we know that A has a positive charge, B has the minus, we also know that C has the positive and D has the minus. What we know will happen is that the A, because it has a positive charge, will come and combine with the negative of the other compound, assuming these compounds break apart, since they'll more likely be ionic compounds. You're going to see an aqueous sign here at the bottom for both of these. So the product here that you're going to wind up seeing at the very end is you're going to have A bound to D, and then C will be bound to B. Retaining the charges here, you can see where the regrouping took place. Since two separate atoms were replaced in this reaction, this is known as a double replacement. The final compound reaction, or the final reaction that you should know about, is going to be the combustion. A combustion reaction usually involves a hydrocarbon, say CH4, for example, or any other version of that. There's only carbon and hydrogen in the compound. You're going to react this with oxygen, and it will produce two prominent compounds, which is going to be carbon dioxide and water. There might be some energy release, but essentially this particular compound is extremely easy to find because you know that you're going to get oxygen reacting and with a compound that only has carbon and hydrogen, and the two products are very distinctly carbon dioxide and water. Now these reactions tend to need to be balanced, and so you'll have to balance it in order to have a full balanced reaction. But these are the 5 reactions that you should be able to identify. So if you're provided a reaction, you want to use the format here in each of these reactions to see which one you've got. A lot of the times the reactions that are typically the ones that tend to be asked often are going to be predominantly the first 4 here, with a huge emphasis usually on a single or a double replacement, but any one of these could be a reaction that they could ask you. So be prepared for that. So what we'll do now is we're going to head over to one of the last sections here involving reactions. There's a couple of items here in the reaction side, so I'm going to group them all together. But the first section here is we're going to need to balance reactions. So these sets of problems are asking us to balance each of these reactions here. And so what we'll see here is you'll have to go ahead and count the atoms on the left side. Keep in mind that the left side is typically related to this arrow here, so everything on the left side is known as a reactant, and everything on the right side is going to be a product. So let's go ahead and balance things out. So what I will do here is I'm going to go ahead and put a line here. This is my left side, this is my right side, and all I really want to do here is go to the very first compound, count the atoms. So here I've got silicon, there's only 1 copy. On the right side, I've got 1 copy, so silicon's balanced. We'll go to the oxygens here. Notice we have 2 on the left-hand side, and we only have 1 over here. So what we'll do is we'll make a copy here of CO. Now we've got 2 oxygen atoms on the right, 2 oxygen atoms on the left. The oxygens are good. So we'll turn our attention now to the carbon. Carbon's here. We've got 1 on the left, but we've got 1 on the right, 2, 3 total. We don't want any odd numbers, so this one here, the SI, we're going to go ahead and convert this. Since there's a 1 here, we're going to convert that into a 2. We'll add another copy of SiC. But the second that I do that, now my carbons are balanced, but notice what happened to my silicons. I've got 2 silicons on the right, but I only got 1 on the left. So we're going to add another copy of the silicon dioxide. And so at that point, we should be in a good spot. Let's take a look. So we'll do the check again. 2 silicons on the left, 2 silicons on the right. Now we've got 2 and 4 oxygens total on the left. We've only got 2 on the right. So what we're going to do is we're going to add another copy of carbon monoxide, another copy. That'll give us a total of 1, 2, 3, 4. Let's go ahead and change color here. So we've got 4 oxygens on the right, 4 oxygens on the left, 2 silicons, 2 silicons. Now we're going to count the carbons. We've got 1, 2 on the right, 3, 4, 5, 6. We've only got 1 here, so the only thing that we can do here is to go ahead and put 6 copies of carbon. 3, 4, 5, 6. Now, what we'll do here is we're going to count the total copies of all of these. So what I'll do usually visually is I'm going to circle the copies. So I've got a 2 here, so I'm going to put a 2. And I've got 1, 2, 3, 4, 5, 6. So I'm going to have a 6 for the carbons. I've got 2 copies of the silicon carbon or carbide, Here we've got 1, 2, 3, 4, so that'll be 4 copies of that. Now, one thing you can notice here, if you kind of look at all of this, notice how all of these numbers in the coefficients are numbers that are even. What we can do here, because this is not the simplest version of this equation, we want to come in here and then divide everything by 2. And so if we do that, now this might be the long way around, but here the number for the coefficient truly is a 1. This is going to be a 3, this is going to be a 1, and this is going to be a 2. So those were the numbers that would originally have balanced this reaction. So you want to pay attention to the numbers in green overall. Let's go ahead and look at the next problem. And so that next problem here is right there in the middle, F2, H2O, HF, O2. Notice we've got a diatomic oxygen, so we're going to save the oxygens to the very end. Same thing here, so this is going to be a little bit of a tricky one, so we'll start here with the H2O, since the hydrogen is not inside, it's not a gas, it's inside the liquid. So what we'll do here is we're going to go ahead and do 2 H's. We've only got 1 H here on the right side, so we'll add another copy of HF. And so that should give me 2 hydrogens on the right, 2 hydrogens on the left. I've got 2 fluorines. I've got 2 fluorines here on the left. And so that means here that I'm going to need to look at my oxygens. My oxygens, I have 2. I only have 1 copy in the water. I will be forced to put another copy of water. That is going to disrupt my hydrogens because now I've got 4 on the left. So I have to add another 2 copies of HF here to bring my hydrogens back to balance. So I've got 1, 2, 3, 4 on the right, 4 on the left. I've got 4 fluorines. I need to make sure I balance this out, but take a look here. My oxygens are balanced on the left and on the right. The only thing that needs to be balanced here is another copy of F2. So if I put my coefficients here, I've got 2 copies of F2, 2 copies of H2O, 4 copies of HF, and then only 1 copy of O2. And so this is my final number that would balance this reaction. Now the final compound that we need to, or the final reaction that we need to balance is the one you see here. And so let's go ahead and do this one. We'll start with the leftmost compound, the first atom. There's 4 carbons, so that means I need to put 4 carbon dioxides here in my formula. So that's a CO2, CO2, and a CO2. So now I've got 1, 2, 3, 4 carbons in the product, 4 carbons in the reactant. I move on to the next atom. That's going to be hydrogens. I need a total of 10 on the left, and I need 10 on the right. Hydrogen only exists in this compound, so I need 4 more copies for a total of 10. So there's 1 copy, 2 copies for a total of 3, 4, and 5. So if I count all of my hydrogens, I've got 2, 4, 6, 8, 10. That means it balances out with a 10 on the left-hand side. So now I'll turn my attention to the sulfurs. I've only got 1 sulfur here on the left-hand side, 1 sulfur on the right. So the sulfurs seem to be pretty good. Now I'll turn my attention to the oxygens. Here I've got 2 on the left-hand side. And over here on the right, I've got 2, 4, 6, 8. And so let's go ahead and write that number down. We've got 8 overall, so I'm just going to put a number here of 8 so I can keep track of it. And then over here I've got 1, 2, 3, 4, 5. So that gives me a total of 5 oxygens here with the water. And then finally over here at the very end, I've got 3 oxygens, and so I'll put that number here. And so I'll write that number here at the bottom, 3. Now if I take all these 3 numbers here, 8, 5, and 3, that'll give me 16 oxygens overall. Since I've got a 2 over here on this side here, some number times 2 will give me 16, so the number here has to be an 8. So if I put an 8 here, that would balance everything out. And then if I go back and put all the coefficients where they need to be, I've only got 1 copy of the first compound over here at the beginning. Here I've got 1, 2, 3, 4 copies of the CO2, so I'm going to put a 4. And then I'm going to go ahead and put 1, 2, 3, 4, 5 copies of the water. And then lastly, there's only 1 copy of the SO3, so those will be the numbers required to balance that. All right, so the next topic is to figure out conversions using stoichiometry. And we've got a problem here right at the very top. And so let's take a look at this. We know that we have a balanced equation, so let's go ahead and write that down, or at least underline it. We know that it's balanced. And what we want to find out here is how many moles. So the unit that we're after here is the unit of moles of MnO4, and MnO is one of the reactants. So we want to know how many moles of this will be produced if 0.7009 moles of Mn are produced. So essentially the question is a little awkward here. We're not going to produce any MnO. Maybe here what we're trying to say is how many moles of MnO are consumed if 0.7009 moles of that are produced. So that will probably make more sense since we've got moles here. Notice the other unit that we're asked or provided here is this one here. So this particular problem is a mole to mole conversion. And so we can get that set up. And so we want to start always with the amount that's provided. That amount that's provided is the 0.7009 moles of the product. So let's go ahead and do that. So we'll start here with the amount that's provided. That will be 0.7009 moles of Mn. And then we're going to set our dimensional. And we're going to need a conversion factor. We do have a balanced reaction right here. So what we know here is that we have a ratio of 3 moles of Mn for every 3 moles of MnO. So the ratio is a 3 to 3. Since we have moles of Mn, I'm going to put Mn in the denominator. So here in this particular case, I'm going to put 3 moles of Mn, and that'll be this part, is related to 3 moles of MnO, and that'll go in the numerator. Is for every 3 moles of MnO. And so at this point, we cancel those items that can be canceled. The Mn can cancel the moles, and so that's going to leave us the moles of MnO. And if we look at the question, they want to know how many moles of MnO we've got. So we've got the problem set up the way we want. All we need to do at this point is to come in here and do the math. So we'll take the 0.7009 multiplied by 3 divided by 1. And so if you haven't already noticed, the 3 divided by 3, that there should also simplify. That will give you a 1 here and give you a 1. So the answer literally is 0.7009 moles of MnO. And since it's a reactant, that means that this was consumed. And so that is the answer to this particular problem. So let's take a look at the next problem here. We've got this equation here for the following, for the balanced equation. Notice it's balanced again. How many moles of BaO, BaO is one of the products, will be produced if 20.5 grams of oxygen. Again, it's a little bit of an awkwardness on this problem here. This is not going to be produced. This is going to be consumed. And so let's go ahead and do this. The starting material that's provided to us, here we've got moles. This is an unknown of the product. And we are provided a starting material of 20.5 grams. Here, notice that we're going to start with grams. So we're going to have to convert this to moles. And so we'll do the following. We'll start with the given. In this case, we're going to start with 20.5 grams of the oxygen. And let's go ahead and immediately convert this into moles. And so to convert that, we'll say for every 1 mole of oxygen, it's going to have a certain amount of mass of oxygen. Since this is O2, each oxygen atom has a mass of 16 times 2 gives us a mass of 32 grams for the O2. At this point, we can go in here and cancel the grams of oxygen, and we're left with the moles of O2. So now we are at a good point where we can go from moles to the moles of that. So here, this is the moles of O2. That gives us this particular ratio here, but we want to know the moles of the product. So the ratio here would be a 1 for the oxygen to 2 moles of BaO. So right here in this area, I'm going to have to put a conversion factor. So I'll extend my dimensional analysis line, and then I'm going to start with the moles of O2. I'm going to bring that and put that in the denominator. So notice here, I've got 1 mole of O2. So I'll put 1 mole of O2 for every 2 moles of BaO. So in the numerator, I'm going to write 2 moles of BaO. And so at this point, cancel the moles of O2. Moles of O2, notice what's left, moles of BaO, and that happens to be the product. So this part is that part right there. So we've set everything up. All we need to do at this point is take the 20, multiply by 1, multiply by 2, and that'll give us number in the numerator. So if I do that there, that'll give us the following. So that'll give us 41 moles of BaO. And in the denominator, I'm going to go ahead and take 32 times 1. So that'll be 32 in the denominator. Go ahead and take that number and plug it into the calculator. Take the 41 divided by 32, and that should give you the following number. So in this case, we've got 1.281 grams of BaO produced, because it's the product that we're looking at. Now, at this point here, this is our final answer. So we're going to go ahead and circle that. But you keep in mind here, when you're doing these kinds of problems, it's important to notice the unit that you're starting with. And if you need to change it from grams to moles, just divide by the molar mass. And then up to this line here, you'll have the unit for this number here to be in moles. And then at that point, proceed as if it were a mole-to-mole conversion. Okay. So the last concepts that I want to talk to you about here are solubility. Now, solubility is something that's going to be fairly straightforward. The thing that you're going to want to have handy for yourself is you want to make sure that you have the solubility table at your disposal. So let me bring that forward. So here is the solubility table, and we're going to reference this here as we go through. So I'm going to bring this down over here to the side, and I'll bring it up as we need it throughout this exercise for these couple of problems. So the first question that we've got here is, how do you tell that a compound is soluble? And how do you tell if it will dissolve if you place it in water? Well, the main way that you can tell, if we bring the solubility table out, is according to this, what you're going to find is when you look along the top of this particular table, you're going to see that you've got metals along the top, and then you've got anions along the left. Typically what you do is you look at the compound that you've got. They're going to give you a formula of some sort. And you look at the first atom, you figure out what it is. And let's pretend that our formula here was NaCl, for example. So you would look here. Sodium is the first atom. So we look for sodium along here and we find it. I'm going to go ahead and just go ahead and put a green here to underline it or highlight it. We've got sodium here, and chlorine, if we look over here, is going to be found right here on the left-hand side. We'll do that too. And what you're going to do is you're going to go where these intersect. And so notice they intersect right here. And so here's what you know. Anytime you see SOL, SOL means that it is soluble, that it will dissolve. Anytime you see INSOL, which are the ones in red on this table here, which is right here, all across, each of these are going to form a solid or a precipitate. The same thing would go here for the ones that say slightly soluble in gray. Those would also dissolve a little bit, but you're going to get a lot of it in precipitate form. So how do you know that it dissolves? When you cross them, it's going to point to an SOL. So make sure you look at that for each of the compounds in your sample set. So let's go ahead and move these out of the way. And so when we look at the two questions that we've got here, you should be able to see that the two questions have already been answered. And so how do you tell? You're going to get a SOL. So SOL is the thing that we're looking for, because this means that it is soluble. And that means that it will dissolve. And how do we identify that if it's given in a reaction? You're going to see that identified with an AQ as the subscript underneath and to the right of the compound formula. Okay, and so when they do dissolve, that's what's going to happen. What if they don't dissolve? Then obviously you're going to form a solid. But when the compounds dissolve, according to the second question, what do they produce? The common thing that you should know here is that they're going to produce ions. That's very, very important. So let's move this over here to the last question here, and let's go ahead and bring this little periodic table down with us. We'll bring it down, and then we'll come over here and kind of look at things. All right, so let's take a look at this last problem here. We've got a couple of compounds. We've already done the first one, so let's kind of do this one more time. We've got the sodium here. We've got the chlorine. It's going to come down. Notice it says SOL, and so here's how you know. Here to here to here, it's SOL. So what we're going to do here is we're going to say, do the compounds dissolve? Yes, we're going to say AQ, and that means yes, will dissolve for that particular compound. let's go ahead and reset the clock here and go to the next compound. We've got AgBr, so we'll look up Ag. Ag in the solubility table is right over here, Ag. So let's go ahead and circle that. And then we're going to go over here to the Br. Br is right here on the left-hand side. And so we'll go through and figure this out here and here. Notice it's INSOL. So what does that mean? INSOL means that it will not dissolve. It's going to form a precipitate. And so we're going to identify this with a subscript of S. And so that means here, this is going to be a precipitate. So it will not dissolve. No, it will not dissolve. Let's go ahead and take a look at the next compound, and let's go ahead and reset the solubility table. And so here we've got that. And so now the third compound is FeOH2. Let's start with the iron. That's going to be the cation, so we're going to look at the very top. We'll look for iron, and we see it right there. Let's go ahead and circle that. So iron. The next compound, or the part of the compound, is OH. So we look for OH, and then we find it here. Let's go ahead and circle that, and then let's see where they intersect. And so notice here they intersect again at a insoluble. So that's going to be that it will not dissolve. So we're going to come over here. We're going to denote here solid. And so here is the precipitate. And so this is not going to dissolve. Okay. And then finally, let's go ahead and reset one more time. And then we'll look at the final compound, NH4 and Br. So NH4, we look up here. Notice NH4 is right here. So we'll circle that. And then we'll come over here to the Br. Br is on the table right here. Circle that and see where they kind of intersect. And so you can see here that these two parts, these ions, will come in, but it's soluble. That means that in water, NHBr will dissolve. And we're going to go ahead and denote that as AQ. And so the answer here would be that yes, NH4Br will dissolve. So now you've got there all of the example problems we've done for the review. Please make sure that you continue with your review before the semester exam. Take a look at the schedule for the semester exam and make sure that you make the appropriate preparation so that you are fully prepared to do excellent on that exam. If you have any questions, see me in class, and thank you for joining.